So, here we are again, in Blender, with a ball staring right back at us. It wants us to rig it, I can tell. Let's not disappoint. Most of the steps for this are going to be the same as rigging the 2D bouncy ball. The only real difference is that we're going to be using quaternion rotations instead of Euler rotations. However, a lot of the animation that might be done with this ball may still move along a more or less 2D path, so we don't want to prevent the animators from using Eulers, because sometimes it may be useful. If you recall from the 2D ball rig, we're going to use 3 bones, 2 of which will be controls. We'll have a control for location and squash and stretch, and we'll have a control for the spin of the ball. The squash and stretch control needs to rotate to determine the direction of the squash and stretch. We'll be using quaternions for that. But the spin control we'll leave up to the animator. They can select their preferred rotation mode from the drop-down menu. So, let's get started. Add an armature, and set it to X-ray and wireframe display, and turn on bone axis display. Name the armature rig. Go into edit mode, and name the default bone main. And adjust its position so that its local axes line up with the world axes, so that the local axes will behave as the animator expects. Now duplicate the main bone to create the counterspin bone, and position and name it appropriately. And make it the child of main. Now go into pose mode. We need to set up the counterspin bone to do the opposite rotation of the main control. Since the main bone is using quaternions for its rotation, this turns out to be pretty easy. Remember that quaternions cover 720 degrees of rotation, so both the top and bottom of the circle are effectively unrotated. So flipping the W component makes the quaternion do the opposite rotation. And happily, this works in the full 3D case as well. So to make the counterspin bone do the opposite rotation, we're going to drive its quaternion components with the quaternion components of the main control. X, Y, and Z will simply be copied, but the W component will be set to the negative of the main control's W component. Let's start with X. Add a driver to the counterspin bone's X component. And let's go to the driver's interface to configure it. Remember that drivers have 2 parts, variables, and what is done with those variables. To drive the X component properly, we need direct access to the X component of the main control's quaternion rotation. You might think we could just select X rotation in a transform channel variable, but you would, unfortunately, be wrong. Remember how Blender uses transform matrices internally? Well, the transform channel variable type derives its information from transform matrices, translating them back into some kind of Euler rotation. So if we used this, we would be driving the X quaternion component with an X-axis Euler rotation, which is clearly not the same thing. Instead, we need direct access to the quaternion component of the main controller. There is a variable type that lets us do this. It's called single property. This variable type allows us to access any user-accessible piece of data in Blender via something called RNA paths. Blender stores all of its data in something called an RNA system. It's kind of like the file system on your computer, where you have file paths, and different pieces of data are stored in different files. To specify the RNA path of the quaternion X component, we first need to specify what object it's inside. In this case, that's our armature. Select it in the field here. Now we need the RNA path relative to that object. The syntax is very different from file paths on your computer, but the idea is basically the same. Thankfully, you don't actually have to learn the syntax. Select the main bone, right-click on any of the quaternion components. Towards the bottom of the menu, there's an item called Copy Data Path. Clicking on it will copy this property's RNA path into our clipboard. Click it. Now go back to the driver. We can now paste the RNA path into the path field with Ctrl-V. If we expand the panel a bit, we can see the full path. However, this is not all we need to do. This path references the entire quaternion, but we need a specific component of it. Thankfully, we can just put .x at the end to get the x component. Awesome. Now this variable is equal to the x component of the main bones quaternion. You can access nearly any piece of data in Blender in your drivers this way. Now we just have to use this variable in the driver itself. We could type in the variable name in the expression field, but a simpler way, when the driver is just going to directly use the variable, is to change the driver type to some values. This is basically like a shortcut that just adds all of your variables together. When you only have one variable, that means it's just going to copy it. Average value is similar, except it calculates the average value of all the variables. Minimum value and maximum value take the minimum or maximum value of the variables. It's all pretty straightforward. All of these things could be achieved with scripted expression, if you wanted to, but these are simple shortcuts for common cases. In any case, let's select some values, and click Update Dependencies. Now if we rotate the main bone a bit, and select the counterspin bone, we can see that it's copying the x component of the main bone's quaternion. Yay! Now, we could go through this whole process over again for each of the quaternion components, but there's an easier way when you need to make a lot of very similar drivers. Right-click on the counterspin bone's x quaternion component. There's an item labeled Copy Driver. Click it. Now right-click on one of the other components, and select Paste Driver. Ta-da! The Y component now has exactly the same driver. Of course, we don't want it to be exactly the same. Right now it's copying the X component, but that's easy to change. Paste the driver on the other components. Now we just have to change the RNA paths. And update the dependencies on all of them. Now if we rotate the main bone, the counterspin bone rotates in the same way. Of course, since it's the child of the main bone, that appears as a double rotation. But we don't need a double rotation. We need the rotation to be countered. So go to the W driver, change it back to scripted expression, and enter the negative of the variable to flip the W component. Now if we rotate the main bone, the counterspin bone doesn't rotate at all. Yay! Now let's set up the squash and stretch. It's the same as in the 2D bouncy ball, just be mindful of the axes. We also need to make sure that the animator doesn't change the rotation mode of the main control, since our counterspin bone depends on it using quaternion rotations. There's no lock button next to the rotation mode menu, but there's a cool trick you can use to lock any field you want. Add a driver. And now change the scripted expression to be 0. Each item in the rotation mode menu has a corresponding number. 0 is the number for quaternion. Now we can't switch the rotation mode away from quaternion. Finally, it's time to add the spin control. Add a new bone, and position and name it appropriately. And make it the child of the counterspin bone. And make the ball the child of the spin bone. We now have a basically finished 3D ball rig. However, notice that the spin control behaves a little bit oddly when there's an extreme squash and stretch. This is because Blender doesn't handle distorted controls very well. So what we really need to do is have an undistorted control that our current spin control copies its rotation from. This means that our current spin control isn't actually going to be the control anymore, so let's rename it to be a mechanism bone. And let's add another bone and name it spin, and position it appropriately. The difference is we're not going to make it the child of anything, because we don't want it to be distorted during squash and stretch. We still want it to stay in the right position, however, so let's constrain it to copy the location of the counterspin bone. This way it will stay at the center of the ball. Now we need to make the spin mechanism copy the rotation of the spin control. We can do this with a simple copy rotation constraint. So let's give this a try now. Stretch the ball and play with the new spin control. Oops. That doesn't seem to work. It's rotating the squash and stretch as well. What's going on? Let's take a look at the copy rotation constraint again. Notice the two menus at the bottom of the constraint? These menus determine what space the constraint operates in. Right now it's operating in world space. What that means is that no matter what a bone's local space is, it will still snap exactly to the same position as the other bone. If we switch this to local space though, then the local space rotation of the bone will copy to the local space rotation of the other bone. Let's take these two bones as an example. They are currently in their zeroed out positions. If we add a copy rotation constraint between them, the one bone snaps to the exact same orientation as the other, despite their different spaces. But if we change the space of this constraint to local, now the bone is copying the rotation relative to its local space. Going back to our rig, we can do something similar. The reason we get the weird result with the copy rotation is because it's doing the copying in world space, which is outside of the distorted stretched space. But if we change it to local space, then it does the copying inside the local distorted space of the bone, and it works as we expect. And notice that this new control doesn't have the weird behavior of the distorted control. Hooray! One thing you may be wondering is why there are two menus for the space of a constraint. The reason for that is because the left one says what space we're copying from, and the right one says what space we're copying to. So if we wanted to, we could, for example, copy the world space rotation of the spin bone into the local space rotation of the mechanism spin bone. That might not seem useful, but being able to choose those two spaces separately can be handy in some corner cases that would otherwise be a pain to deal with. Anyway, now the functionality of the rig is done. We just need to assign the control shapes. Let's move the mechanism bones to their own layer. And I've already created the shapes. So let's assign the main control bone shape, and then the spin controls shape. Oh my, that's a little bit too big. Let's go and edit the mesh to be the right scale. Oh, and we need to lock the location and scale of the spin control. It's only for rotation, right? And let's turn off X-ray and axis display on the armature. Now let's test. Oh my, the spin control doesn't stretch with the ball. I guess that's to be expected, but it doesn't look right. Fortunately, Blender has a cool way for us to make it look right. If you go back to the bone shape panel, you'll notice that there is an at field under the shape field. This field allows us to choose a different bone that the shape will use as its position. The shape will still be for the spin control, but the appearance of the shape will be based on a different bone. It's kind of weird, but it's useful for situations like this. Select MCH spin for the at field. Cool! Now it looks a lot more like the animator would expect. And now, the rig is done! Congratulations. Yay!